Hey, good morning, sixth graders. Today we're going to be going over lesson 12 in unit 5. This is relating equations, tables, and graphs. And the lesson objectives are make a table and graph based on the equation, and then relate equations, graphs, and tables for constant change situations. This looks really complicated, but it's really not. And I'll teach you guys exactly how to make this look like a piece of cake. So we're going to start, I highlighted it down here, page 213. That's where we're starting. Okay, so let's get into it. So 3 ways to represent motion at a constant speed. Suppose a high-speed train travels at a constant rate between Greenville and Orange Lake. Let T be the number of minutes elapsed. Let D be the number of miles the train has traveled. The variables D and T vary together. Their relationship is represented by the equation D equals 2.5 times T. So remember, when things vary together, it means that they change together at a constant rate. So for example, in lesson 11, we learned that every second that passes, distance is moved, right? And those move together. We're going to do something really similar here. We're going to talk about minutes elapsed in time, and then also miles traveled in distance, right? So we have our T's, we have our D's. So this equation right here is basically saying that distance is equal to 2.5 times whatever the time is. So for example, at 0 seconds, there's no distance traveled. But at 1 distance, or 1 mile, there was 2.5 distance traveled, or miles traveled, right? So let's go ahead and write that into our table, because that's useful information. Let's do it in blue. So for 0 seconds that have passed, 0 miles were traveled. For 1, so if I plug into this equation, 1 for T, that would be 2.5 times T, which is 1, right? That's just 2.5, or 2.5 miles. Now what happens if I let T be equal to 2? Well, that would be D equals 2.5 times 2, right? I'm plugging that number in, or that letter in for that number. So 2 times 2.5 is 5, right? So that's what my D would equal 5. 3 times 2.5, that'd be 7.5. 10, 12.5. Hang on, my dog's squeaking toys. Just a second. Okay. Awesome. So now that we have this table, we can definitely take a table and put it into a graph, right? Let me get rid of some of this work over here so that I can just... So we can take this and we can plug it into this table, right? So we have 0, 0, and then we go to, let's make this a big, huge dot. 0, 0, and then it goes to 0, 1, 2.5. Oops, that is not 2.5. Then it goes to 5, and then it goes to 7.5, and then it goes to 10. That's not 10. It's really important that these are accurate. And then it goes up another 2.5, and then there. Okay. Okay, now they're graphed. Does it make sense to connect these points on the graph? I think yes, because the line gives us like an idea of what that's going to look like, right? I can't make it perfect, but it's close. It's a straight line, right? And it would continue to go on forever if I could. I mean, I could plug this in for 1,000, right? I don't have to, and I don't need to, but it could go on forever. So I'm going to put an arrow on that. Awesome. So draw a unit rate triangle in your graph. Let's do this in green. My unit rate triangle would look like this, which is over 1 up 2.5, right? The height of this would be 2.5. Awesome. So what is the speed of the train in miles per minute? That is, what is the unit rate? So for every one, what's the time? 1 minute. How far will it travel? And the correct answer is 2.5 miles per minute. Miles per minute. Okay. So discuss how T and D are related. So if we were in class right now, we'd be talking about what is the relationship between D and T. And what I mean by that is, how does D affect T and how does T affect D? If I have the distance, can I figure out the time? If I have the time, can I figure out the distance? Yes, of course, because I have an equation. That equation is telling me that for every D, I have 2.5 T's, or 2.5 times T's, right? Okay, so let's move on. So, let's talk about, is the change constant? Superhero Supplies Inc. produces different superpower soups. In the factory, each type of soup flows into a different vat, or a vat is like a container. So let T be the number of seconds elapsed. Let V be the number of liters of soup in the vat. And for each vat, V and T vary together and are related by an equation. Okay, so vat 1 is V equals T squared. Vat 2, so each of these soups give you a special power, right? So super strength, X-ray vision, flying, lightning speed, invisibility. Okay, cool. So let's figure it out. So number 7, vat 1 is V equals T times T, or T squared. So I can look at this and I can easily say, anything that is V will end up here, and anything that is T is over here, right? So if T is 0, then obviously V is 0, right? 0. So this would be 0 squared, which is 0 times 0. What is 0 times 0? It's 0. Now V is just equal to 0. Same thing. Let's do it with 1. V is equal to 1 squared. 1 squared is just 1, right? Okay. Let's try another one. 2 squared. Oh, that's 4, right? 2 times 2 is 4. How about 3 squared? 3 times 3 is 9. 4 squared. 4 times 4 is 16. 5 squared is 25. 6 squared is 6 times 6 is 36. Okay. And all I was doing here was I was just plugging into this equation up here, right? I literally just said whatever is T is here, and whatever is V is over here. That didn't work. Well, those are supposed to be the same colors. Okay. So now I can plug those in over here on the graph, right? So I had, start over here, 0, and then I had 1, 1, and then I had 2, 4, and then I had 3, 9, and then I had 4, 16, so I'm just coming over 1 and going up 16, whoops. Getting sloppy. And then I had 25, and then 36, right? Which is right there. Okay, now I've graphed those. So plot the points, connect the points if it makes sense to do so. It almost always makes sense to do so. Anytime that it goes in order of 1, 2, 3, 4, 5, 6 on your x-axis, you're always going to want to connect your points. The only time you really don't want to connect your points is if there's really no correlation at all, or if you're not looking for something that's sequential. So here we're going to connect these points, maybe, and it's going to go up like this. I'm sorry, this isn't perfect, nor would it be in the classroom, right? Okay. So that's what it looks like. So is the soup flowing into vat 1 at a constant rate? Is this constant? The correct answer is no, this is not constant. And the reason is, if I look at these values that go from here to here, and here to here, and here to here, we're noticing that they are not the same. This blue one is not the same as this purple one, right? This is 1 over 1, a rise over run of 1. This one is over 1 up 1, 2, 3, 4, 5, 6, 7, 8, 9. It grows 9 here. The height is different between here and here and this tiny little one, right? And they're all different. Each of these are different, right? So that's not constant. We cannot say that those are constant speeds. All right. Moving on. So let's do VAT 2 and 3, and these are pretty simple, right? For every t that I have 5 times that will get me v. 0, obviously, that's just 0. The only time that it wouldn't be is in a case like this. So let's take a look at these two equations. I'm going to call this one the blue equation and this one the green equation. And so the difference between these is there's a plus 3. VAT 2 is just v equals 5t, but VAT 3 is v equals 5t plus 3. So over here, 0 is obviously going to be 0, but if I plug in 0 here for this t, that's 5 times 0 plus 3. So it will start with 3. Whoops. You see that? Okay, let's go back over here. Let's do these in blue. And I'm going to zoom in so I can write easier. Okay. So if I plug 1 in for t, right, I have my t. If I plug 1 in for t, I just get 5. If I plug 2 in for t, I get 10. And 3, 15. See a pattern here? We can all count by 5s, right? I hope so. All right. So this looks pretty constant. Things are moving 5, 5, 5, 5, right? Let's see if it's the same here. Let's see if this one is constant. So I'm going to plug 1 in for t. 1 times 5 is 5, plus 3 is 8. 2 times 5 is 10, plus 3 is 13. Whoops. 3 times 5 is 15, plus 3 is 18. Sorry. 4 times 5 is 20, plus 3 is 23. Then 5 times 5 is 25, plus 3 is 28. 6 times 5 is 30, plus 3 is 33. Let's graph these. We can put them on the same line, right? And the reason that I can do that is because these guys, and I'm going to do this in yellow, these are the same. 0 to 6, right? It's my x-axis down here. Whoops. Okay, so let's go ahead and graph these. I'm going to do, the first one is blue, and it is 0, 0. Let's make this bigger. And then 1, 5, 2, 10, 3, 15. Whoops. Come on. Meh. Leaving it. And then 20, and then 25, and then 30, right? And again, I'm just graphing this over here. 0, 0, 1, 5, 2, 10, 3, 15, right? Just graphing that stuff. Okay. Let's do the same thing with, well, let's connect those real quick. Connect. My line is not super great. I apologize, guys, but it's the best it's going to be. Okay, let's graph this one. Let's do this one in green, because we said we were going to call that the green line, right? Okay. Same thing, except for we're not starting at 0, 0. We're starting at 3, right? And then we're going up to 1. 8 sounds right. 1, 8. Nope, that's not correct. 1, 8, 2, 13, and then 3, 18, and then we have 423, and then we have 528. I'm sorry. And then what else after that? 633. Right there. Okay, let's connect those lines, and let's do it with a tiny little green line. So I'm going to go here. Okay. So I have those lines, and I just wish that those looked more straight, but I don't know what to tell you. So these lines basically are the same. They're the same lines. They just start differently, and they just have a little bit, they don't really have a different pattern, right? These are both 5s. These all go up by 5. From 3 to 8 is 5, to 13 to 23 to 28 to 33. These are all plus 5s. Same over here. These are just plus 5s. I'm just going up by 5. From here to here to here to here to here. So these are constant rates, right? So number 13 says, tell whether soup is flowing into the vat at a constant rate. And the correct answer is yes for both of them, right? They're both flowing at a constant rate. Okay. So what does the 5 in V equals 5t tell you? What does that mean? I want you to think about that for a second. What does the 5 in the V equals 5t tell you? If you said, and I'm going to change this. If you said the rate of flow for the soup in liters per second, you're correct. It's the rate. So let's write that, the rate. And again, you should be writing all of this into your math notebook, right? I shouldn't have to tell you that at this point. So the rate of flow for the soup in liters per second. What happened? I'm just going to do capital L per second. No, I better spell that out. I'm sorry, guys. That's just science language. That's how we would write that in science. Liters per second. Okay. So what is the 5 in V equals 5t plus 3? Well, it tells you basically the same thing, right? That 5 is the flow rate in liters per second, and 3 is the number of liters of soup in the vat at the start. So at the beginning, it already had 3, right? It'd be like if you got a weekly allowance of $5 per week, and T is the number of weeks, because that's time. If you got paid $5 per week and 3 weeks had already passed, but you already started with $3, you had $3 from Christmas. Doesn't matter. That's your starting rate, right? So let's write that. Let's do this one in purple because we can. Do this size. All right. So 5 is the flow rate. Three is how much we started with. Now let me ask you a question. Can you start with a minus? Could I say 5t minus 3? In this situation, no. But any other situation, yeah, probably. And the reason no in this situation is because we're talking about liters. We can't have negative liters. We can't owe something liters, right? But I could start with negative $2 in my bank account. I could do, I earn $5 per week, but I owe dad $2, So that's how it would be. Okay. Let's move on. Oops. This might be our last page, right? It's pretty simple. It's pretty straightforward. Okay, now let's take a look at these two. VAT number 4 and VAT number 5. So I have V equals, and let's do these again in blue and green. Let's not switch it up like that. So I have 2t plus 10, and on this one, I have 3t plus 10. So 2t plus 10, 3t plus 10. Do you think that these are going to be constant? Think about that. Let's check it. So let's do some plugging in and some math because it's fun. Okay. So if I have 0 times 2, remember I'm just plugging this in here and I know that because this is t. Okay, 0 times 2 is 0 plus 10 is 10. 1 times 2 is 2 plus 10 is 12. 2 times 2 is 4 plus 10 is 14. You get the drift, right? 16, 18, 20. Let's check it with 6. 6 times 2 is 12. Plus 10 is 22. And yep, that's a good pattern. All right, let's go over here and do the exact same thing. We're plugging these numbers into t. Okay? So 0 times 3 is 0, plus 10 is 10. 1 times 3 is 3, plus 10 is 13. And then I have 16, 19, 22. Let's check it again. 5 times 3 is 15, plus 10 is 25. 6 is 18, plus 10 is 28. Okay. So these are just getting greater by 3, right? This is plus 3 is kind of the rule. And over here we had plus 2 is kind of the rule. The reason that I say kind of is because I don't actually know. It is the rule. There's no kind of about it. Okay, let's graph these. Same thing that we did before. Okay, so I never really started at 0, right? That wouldn't really make much sense. I started at 10 because over here I have plus 10. right? Nowhere in there does it say 0, 0. So I'm going to start here, 10. And over here I'm going up by 2s, right? 12, 14, 16, 18, 20, and 22. And if I connected these, it would look like this. Okay. That was one of my better lines. What do you know? Same thing over here. We're starting at the same place, right? We're starting at 0, 10. Except for this one's going up by 3s. So there's 3, 13, 16, 19, 22, 25, and 28. Perfect. And then if we make this, it looks like this. Not perfect, but does the job. Okay. Are these constant? Let's talk about constant for a second. These are not going in the same direction, but they are both constant. So I want you to write yes for both of these, because these are both moving at a constant rate. And if we go back up to the top where we talk about what is constant, did we talk about constant up here? Maybe not. Oh yeah, here it is. No, we really didn't. So constant, anything that is constant means that it's moving at a rate that does not change. There's no change in this. So like this one changed, right? And we decided that this one changed. That's right, changes. It goes from 1 to 4 to 9 to 16. There's no rate there. It's getting bigger and bigger and bigger and bigger every single time. But here, it stays the same. Here, it stays the same. It goes 3s, 3, 3, 3, 3, 3, 3. It just keeps going in 3s. This one, same thing. It just goes in 2s. These are just getting a little bit bigger by the same rate. It gets bigger, but it gets bigger in the same rate. Okay, so let's talk about what do the 2 in v equals 2t plus 10 and the 3 in v equals 3t plus 10 tell you? What do those coefficients tell you? And it's the same thing as what we just talked about. It's talking about the rate, right? Let's just talk about liters per second. Because that's what a rate is, right? And then what does the 10 tell you? The 10 tells you where it started, right? So where it started. And if we look, that is where they both started, right at 10, right? Okay, guys, good work. Thanks for thinking with me. We'll continue on to lesson 13 on Wednesday. I posted your homework. It should be good to go in OneNote. Please let me know if you have any questions. I would love to talk about this with you. This is something that I used every single day in science when we were graphing and making observations. So, yeah, good luck. Have fun. Let me know if you have any questions. Talk to you later.